Hi, I'm Will Starkey, and this is my lab report for the Physics 1 first lab. What is this lab about? This lab was all about observing a constant velocity motion across a period of time. To do this, I rolled a little wheel across the table along a meter stick to extrapolate its exact position over a certain time so we can get that constant velocity. To get this constant velocity, we used a program called Tracker, which can let us precisely get the points of data so we can correctly calculate the velocity of the object. Also, we created a model to compare to this actual velocity to see if theoretically it is the same as our actual. Now, we also need to evaluate different principles of physics for this lab to make sense. For instance, we need the momentum version of Isaac Newton's second law, which states the change in momentum over the change in time equals our net force, which we will get into later. And here's a little sneak preview of what is to come. Now, using Newton's second law, we can evaluate that the change in momentum can be equaled to the change in velocity. Now, if we look at that change in velocity meters and we divide over that delta t, we can see that actually our F net is our change in velocity over time. And if this change in velocity is going to be zero, because if you have a constant motion, the velocity therefore isn't changing, which means the net force actually is zero. So we can use this concept to look at how our model shouldn't have our velocity increasing, have any acceleration, but a constant velocity. Therefore, if we look at, let's say, a position versus time graph, it should just be a linear function going across diagonally. Here is the video in which I got my data from. As you can see, there's a wheel going across the meter stick, and using tracker, again, we analyzed and we saw that constant velocity as it moved along the meter stick. Now, for the actual model of the experiment, though, we have to code in what our velocities should be. Now, in the code, if you'll look, you'll see a delta t value. This delta t value is very specific because I had to match it to how many steps or how many data points I had in my actual data. And I did some calculations to figure that out, and I found that this number allows the code to run a certain amount of times to where it'll only give me as much data as I have for my observed, which makes me line up the graphs far more easier and correctly. We also see if we look down here, the vector, which is the velocity of the ball, all right, that shows our constant velocity going as the ball will move in time. And as our position, it'll move the same since the velocity is constant. Here is the actual model of the ball moving. As you can see, it moved from the initial point, this yellow point, to the blue space. Now, it just goes in one direction, as it's just a constant velocity in one direction. And a constant velocity can't change, it can change direction, but, or constant velocity can't change direction. It can be in any direction, though. Here is the data we got. As you can see, this red line is the expected values that we got. And as you can see, it's very linear and very straight because it is a constant velocity. It shouldn't have any exponential function as that would lead to an acceleration, which a constant velocity would not have. But if you look at this blue line that is under it, you can see how it has a lot of bumps in. Now, this can be due to some errors in the equation. For instance, there was a slight friction on the wheel as it moved across, which led to some differences. Also, when we are extracting data off a tracker, it's not completely precise. Now, what would happen if we change the axis, let's say? Well, if we change the axis, the experiment would still be the same. Velocity is always going to be the same magnitude if it's constant, okay? So it doesn't matter what direction we're going in. But if we're doing the velocity, if we look at it as a different set of axes, it'll just be pointed in a different direction relative to that axis. Because, as it says on this third point, the direction is based on where the axis is, what we define as the positive and negative directions. Now, what does this mean? How could we predict how many forces were at play since our net force were equal to zero? Well, we know now that our constant velocity was zero. Therefore, our net force must be zero because there was no acceleration, there was no change in it. We don't know how many forces acted on this object, though, because the net force is zero. We don't know if it was two forces coming at each other that made it equal zero. And we don't know if it was maybe one from the top, one from the bottom that led it to equal zero. Because our net force just shows us the change in velocity. Because Newton's second law states that that's what the net force equals. F net equals the change in momentum over change in time. But if there's no change in momentum, then our net force equals zero. Thank you for listening to my lab report.